All right, number 41 here. We've got a problem where we've got a stone tied to a string of length 1.10 meters. All right, so L is equal to 1.10 meters. And we know that it's swung two different ways at the same constant speed. All right, so in one situation, it's spun in a vertical circle. All right, radius, of course. This is L, so it's R. R is equal to the length of the string, 1.10 meters. And in the second case, it's whirled around in a nearly horizontal circle, it says, at the same speed. All right, so in each case, it's whirled around. It has to have centripetal force acting on it. And in fact, if it's at the same speed and it has the rock or the stone here has the same mass, it has to have the same overall centripetal acceleration, right? So the net force has to be the same, so the tension has to be the same. Not exactly. So let me stand back on that. But we know that the maximum tension in the string is 15% larger than the tension that exists in the string when the circle's horizontal. All right, so down here at the bottom, we know that that is going to be where the centripetal force is at a maximum, okay? And we've discovered before that this maximum centripetal force, I'll run through it here, we know that net force is equal to mv squared over r, and we know that net force is equal to, taking the center of the circle to be the positive direction. In this case, it's pretty easy because the top of the circle is in the upward, in the typical positive direction. And so here we're going to have tension in the string acting this way, and we're going to have mg acting downward. All right, so down here we see that the net force is going to be equal to tension in the string. I wrote it as T up there. Let me fix that. All right, we like to do it this way so we don't confuse it with rotational period. So Ft that way. So Ft minus mg. So when we put those together, we get where the tension is at a maximum. Here, tension is equal to m times the quantity g plus v squared over r. And we discussed earlier that looks kind of like the elevator equation. So that's where it's at a maximum. Just to refresh your thinking, we know that at the top, just as an aside here, at the top, the tension is going to be equal to mv squared over r minus mg. And you can go back and review your notes to see why that's true. All right, so I guess the idea that they have over here for the horizontal circle is that the centripetal force, the net force, is equal to the centripetal force, which is going to be equal to mv squared over r, and the net force is just going to be the tension in the string. Now I have a bit of an exception to that. We can explore that at a later time, but for our purposes now, we can just see that the centripetal force tension is going to be equal to mv squared over r. Okay, by setting those two equal to each other. Those are getting a little crowded, but hopefully you can pick out what we're doing there. All right, so here, let me fix this here. I just did it again. Force of tension there. All right, so the tension force is equal to m times g plus v squared over r. We're actually going to have to blow that back up. So let me just rewrite it. No, we're not. Sorry. All right, so what we're going to see is, or what we've been told, is that this maximum tension right here is going to be equal to 1.15. It says 15% greater than this, which just means that it's 1.15 times as great. All right, so we know that m times g plus v squared over r is going to be equal to 1.15 times mv squared over r. And for convenience sake, we will see that mass is canceled. And now we're trying to find the speed, right? So we will say g plus v squared over r, so we'll subtract v squared over r from each side, and we'll show that g is equal to 0.15 v squared over r. Multiply each side by r, divide by 0.15. We're going to get, and take the square root, we're going to get v is equal to the square root of gr over 0.15. And the radius we know, and g we know. So v is just going to be equal to the square root of 9.8 meters per second squared times 1.10 meters. Give the precision that they gave us, 3 sig figs, divided by 0.15. Quick dimensional check, meters squared per second squared. Square root is going to be meters per second, which is what we're looking for with a velocity. So we just put this in the calculator, and I get that v is equal to 8.48 meters per second. And that checks out with what the book says, so we'll call that one a wrap. It's a wrap.